good evening, good morning, wherever you are. Welcome to Math 1031. This will be the weeks 12 and 13 class. We'll finish it all up in one shot. It actually kind of works very nicely here. My name is Ian Coates, and welcome there to basically our last class. This will cover weeks 12 and 13. And interestingly enough, we finish off here, and I encourage you in your professional career after you graduate from Georgian and go on and do your degrees and become world famous. I encourage you between then and now to go on and take another statistics course, because where we are leaving this course, it's a great springboard to jump off of. And you'll see what I mean there. So today there, as the picture implies, at the end of this here, we're going to be able to actually compare apples and oranges, which kind of goes against what Mama taught us. You know, the whole thing here is that you can't compare apples and oranges, but you really can. And we're going to show you guys how. First, you're going to have to print off a copy of the Z table PDF, and that's included in the Week 12 folder. You will need to do that, so pause the video, make sure there that you have a paper copy of it, because basically you're going to be taking two fingers and kind of, I don't know, one's going to come from the top, one's going to come from the side, and you're going to meet in the middle kind of a thing. Sorry if that doesn't make any sense at this point in time, but you'll see what I mean soon enough. Okay, so for about the first half of the PowerPoint, a little bit of review, but then the second half there, we're going to get into the good stuff here. So we're going to fly over the first half. All right, let's go. And as well, for you viewers out there, do not view the PowerPoint in slideshow. I say that, and I'm a bit strange in that I like to utilize the whole space. And today there, you're going to see I'm going to be moving things around, my own little haphazard, crappy animation, but you'll see there, it'll work. Okay? All right, so today there, we're going to review samples and populations. We're going to look at probability like we did there last week when we were talking about, you know, pulling marbles out of bags and the number of tens or hearts or jacks or aces in a deck and all these kinds of things, right? What's the probability of pulling, you know, a green marble as opposed to a yellow marble? These kinds of things. And we're going to take the whole idea of probability a step further. We're going to look at the normal curve, which we introduced slightly, okay, before test 2, okay. We didn't really go too hard into it. We looked at, you know, the percentages involved within the first standard deviation, 34%, and then the second standard deviation, 95, and third standard deviation, about 90, you know, 90, 97, 99, somewhere in there. You can get in there. And we'll have a look, okay? And we'll show you guys all these, all right? We're going to take the normal curve and we're going to go and move on with it, which is the whole point here of comparing apples and oranges, okay? Identify the properties of normal distribution. Something there called a Z value, okay? They're easy to calculate. Z is just another word there for counting standard deviations. We'll get there. Find the probabilities for normally distributed variables by transforming it into a standard normal variable. That's what we're going to be doing there, and we'll answer some questions along the way. All right, let's go, shall we? So this is all review, the first little bit there, so we're going to fly. Inferential statistics, right? You're inferring. Right, there's a degree of uncertainty there, right? If you're going to take, remember there at the start of the course we were talking about the whole idea is that if I want to find out who the people think are going to win the election, well, you don't go and ask every single person in Canada. You don't have the money, the time, the resources, no. So what do? You take a sample of that population. 100 people, 200 people, 1,000 people, 5,000 people. Of course, the more people that you poll or ask, you're going to get a higher degree of accuracy, right? But when you're trying to predict 1,000 people onto 40 million, yeah, there's going to be some uncertainty there. So this is the whole idea behind inferential statistics. Allows us to draw conclusions about theoretical principles that go beyond the group of participants in a particular study. So you're projecting the results of 50 people onto a greater population, right? So you are inferring, okay? And you're going to see there in statistics, you guys go on and take another statistics course, you're going to see there that like in chemistry or all these things, right? We like to calculate the percentage error because error is a bad thing. Well, in statistics, especially inferential statistics, you can't do it without error. You can't. If you're going to take 20 people and do a study on them and then project the results of that 20 people onto a larger population like a country, you're going to have error. And you learn to live with error when you're dealing with statistics. Differences there between a sample and a population. Population here, the entire set of things of interest. Okay, the entire piggy bank of pennies, the entire pop, okay, of Canada. Sample is a part of the population, right? A handful of pennies from that piggy bank. 100 men and 100 women who answered an online questionnaire about healthcare usage from the Canadian population. Right? Got it. Let's go. Why samples instead of a population are studied? We've answered this meticulously, right? It's all about resources. And who has the resources to go and actually ask everybody what they think? We don't. Okay? So it's all, and the more you guys get into it there, the more you'll see. Might as well just boil it right down to brass tacks and say it's all about money, money, money. Do you have the money to interview 40 million people of Canada? Do you have the time? Do you have the resources? How are you going to do it by car? Are you going to, email? How are you going to do it? Okay. Now, sampling methods. Okay, now, again, this is review here. It's all about randomization, right? Sampling method is randomized if every element in the population has an equal chance of being selected for the sample. Randomizing is everything. Because if things aren't random, if there is some type of logic, then that means that there are other powers at play. And therefore now it can't be classified as a truly autonomous scientific study. Things, you have to let the numbers sing. So randomization is a huge concept, okay, when you're talking about populations, samples, doing studies, these kinds of things. You do not want to involve the researcher in pretty much any way, okay? There are several different methods researchers can use in order to ensure a sufficient degree of randomness. You've seen most of these there. Simple random sample, cluster sampling, stratified random, multi-stage random, convenient, systematic. Just going to go quickly over them here. The whole idea, simple random sample. This is the truest form of randomization because every element has an equal chance of being selected, right? Draw names from a hat, okay? You can use computerized random number generators to select values for the sample. Okay, simple random sampling. Genius. Stratified random sample. So in certain populations, there are a particular attribute of the data, example gender, whatever, will potentially strongly impact the value of the variable being analyzed. Weight. Okay, there is a correlation there between gender and weight. Okay, thus it may be considerable or desirable there to have a sample that reflects the proportionate diversity of the population with respect to that attribute. So here you've got this population, greens and blues. So, you might random sample. Well, the whole idea there that when you flip a coin, right? We talked about this there last week. 50% chance of getting a head, 50% chance of getting a tail. But if I just do an empirical study right now and I just flip my penny there 10 times, I could get 7 heads and 3 tails. That's not 50-50, but that's what happened. So in this case here, in this population, ideally, if I'm randomly going to select people from it for my study, you know, I'm going to choose 10 people. Well, just like the coin, I might get 7 blues and 3 greens, which is not proportionate to what I want. So what you do now, stratified, you break them up into their different strata. There's my greens there, and then now you draw, and you'll see there you do get 50-50. Beautiful science. Beautiful. Systematic sampling, we've covered this there. You guys will remember that formula. Okay, trying to find K. All right, it is possible to achieve a seemingly randomized result without actually using randomization. This is called systematic sampling. Okay, where you use your K value, and your K value, which is based on the number of data points there, will tell you how many spaces there do I need, and then I draw another candidate. So 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3. Okay, so these kinds of things right here. Good. Sorry if I'm flying too fast. This is all review kind of anyway, right? Where do we go here? Good. Cluster sampling. In some populations, it is very convenient to break the population up into clusters that reasonably reflect the population, right? I think the example I used there way back in the start of the semester was, neighborhoods, right? This neighborhood, if you had the city here, okay, and cities tend to be, diverse. You have different areas, ethnic areas, financially strated areas there, and however you want to break the city up, and let's just go by neighborhood, right? So, and generally people in the same neighborhood think alike, all right? So, you could pull populations out into samples this way. So in some populations, it's very convenient to break the population up into clusters. Selecting a sample requires randomly selecting sufficient number of these clusters and then sampling every element of the selected cluster. Okay. Multi-stage random sampling. You can obviously see what's happening here. Okay, I've got mashed potatoes here. You stratify them, and then you can pull from there, right? So when a population is very large, it may be first necessary to narrow down the pop into smaller groups before employing one of the sampling techniques. Perfect. Convenience. This one here you can have trouble with, but if this is all you got, some data is better than no data. Convenience sampling is sometimes used to collect a sample by selecting elements of the population who are readily available and willing to participate. Now, are these people who are ready, willing, and able to participate in your study, are these the ones there that you want? I don't know. We'll see. What about the other people there that are not willing and not able there to participate? I want those people too, but they don't want to be in my study. All right, well, I got to do this study because we're investigating the the effects of cobra venom on on whatever it is. Okay, make up something, but the study has to go on, right? So convenience sampling is sometimes used to collect a sample of by selecting elements of the population who are ready, willing, and able to participate. While this is an easy and cost-effective method for collecting a sample, it does not generally produce a random sample and is often very biased. Problemo. Okay? Sometimes to the point where the sample is useless for drawing any inference about the population. Okay? And you have a look here. Here I've got orange, blue, and green. I've got all these different characteristics out here, right? But the only people that want to talk to me are, well, greens are all over me like a duck on a June bug. I got a couple blues who want to talk to me, and sadly, no oranges want to talk to me. So you see here how, not having any orange in my sample, I know that I'm missing the boat here. I'm missing information, and it'll have to be noted there in my study. All right. So again, this one here, People who are ready, willing, and able to participate may not be the ones that you're entirely interested in talking to. All right. Example here, professor wishes to know what students think of the cafeteria food on campus. So she distributes a survey to students in the cafeteria during lunch, asking them to rank cafeteria from 1 to 5, based on a variety of different criteria. So you can see how this one here could create bias. The people who are eating in the cafeteria probably like the cafeteria. That's why they're there. What about the people who ate at the cafeteria once and have never gone back? What about the people there that have never been there? You know, there's all these different aspects to this study here that a researcher is missing. All right, and it needs to be noted because missing information, that's the first thing critics will attack your study with. So again, which sample method to use? You guys can have a read of this. The answer there that I came up with there was a simple random sample. You guys can have a look at that as well. Pause the video. Here's another example there. School board wants to study the effectiveness of team teaching. In this case here, they'll use a multi-stage random sample. All right. Let me know what you think on those ones there. Just things there to make you go, All right. So we've done this bit of review here. It's probably unnecessary, but just to get you guys into the whole aspect of a sample as opposed to the population. Okay. Now, the rest of the PowerPoint is not going to be about, random samples or stratified random samples or convenience sample. Just wanted to kind of throw that in there as kind of a refresher. All right. But where we're going to be moving on is what we call the normal curve. Let's go. So just remember there that there are experimental studies and observational studies and surveys and consensus. Okay, different kinds of things here. Okay, you'll see there, the experimental study there where you have a control group as opposed to a group there that received the medication. The control group, of course, did not. You look at the results. Observational studies, behavioral studies there, somebody there with some type of mental illness or physical disability or, whatever it is there, behavioral issues there, observational studies, just watching, observing, okay? And in neither case there is the experimenter directly involved in the experiment. All right, they're just kind of watching it go by. Then we have surveys and census there. They experimenters will send these out to people, and the return rate is not high. I think it's like 0.3%. So you don't really get a huge return on sending out surveys, but it's also a valid resource. Okay. Last week there we looked at probability, okay, and that we can never really know anything for certain. Okay, you can flip a coin, and let's say you flipped a coin 20 times and you got heads 20 times. That has absolutely no influence on the 21st flip. All right, you don't know what's going to happen. That's the uncertainty of life, right? Which is very important to note there in inferential statistics. Expected relative frequency of a particular outcome. How many possible outcomes are there? So used for discussing probability for the result of an experiment. Heads or tails. How many outcomes? 2. Right? 6-sided dice. There's 1, 2, 3, 4, 5, 6. You roll the dice. How many outcomes? 6. Right? What is the expected relative frequency? Excuse me. Number of successful outcomes divided by the number of total outcomes you would expect to get if you repeated an experiment a large number of times. So, here, example there, 8 heads, 4 tails, 12 total, right? And 2/3, 8 out of 12 were head, 4 out of 12, 1/3 were tails. Long run relative frequency, interpretation of probability. understanding of probability as the proportion of a particular outcome that you would get if the experiment were repeated many times. In this particular case, think of the law of large numbers, right? I flip a coin, 50% heads, 50% tails. That's what you should expect to see. Okay? All right. Figuring probability, determining the number of possible successful outcomes, determining the number of all possible outcomes. Now, going back into successful, what are you looking for? If I'm rolling a dice and I'm looking for a number less than 3, so I'm looking for rolling a 1, a 2, or a 3, whereas a 4, 5, or a 6 would be an unsuccessful outcome. I'm not looking for a number greater than 3, right? Determine all the possible outcomes. Divide the number of possible successful by the number of all. Okay. Something there with a probability of 0 has no chance of happening. Something there with a probability of 1 has a 100% chance of happening. If you have a jar that contains 100 jelly beans, 9 of the jelly beans are green. What is the probability of picking a green jelly bean? Well, I'm looking for 9 divided by 100, so I have 0.09, right? Or 9%. Okay? That kind of a thing. Good. Let's go. Now we're kind of moving on into the new stuff. All right? In statistics there, you're going to see there that P is a symbol there for probability. And you're going to see P coming up. You'll see it there on the assignment. You'll see it there on the quiz as well as the test. And P just means probability. Usually written as a decimal, okay, but can also be written as a fraction or a percentage or even a ratio, okay? The whole idea there that the decimal, like if you see something like 0.055, oops, sorry, 0.055. You look at that number there. That number there means 5.5%, right? Times by 100%, and you get 5.5%, right? So usually that's how percentages are written, okay? But they can also be written as a fraction, a percentage. And you'll see there that in this case here, P, probability, is less than 5%, right? The alligator's mouth always points to the greater side, so if that alligator mouth was pointed there towards the P, the probability that this event is going to happen is greater than 5%. But in this particular case here, the probability of a particular event happening is less than 5%. That's what that means. Okay. So, key points, we've looked at a population, okay, population parameters. And we've looked at all these there. We've looked at the mean, the variance, the standard deviation of a population, right? The mean, here we're talking about the central axis, right? Where are the majority of the people thinking? Oh, they're thinking in and around, you know, the if you have all these different numbers, the majority of the people there are looking at around 60, whatever your value is. That's where the majority of the people are. That's your central axis. But then you're talking variance and standard deviation. Here we're talking spread, okay, of the data, which we'll get into, okay. We're able to calculate it. You guys did very well there on quiz 2 and test 2, calculating there your standard deviation and variance, okay. We're going to take that a step further, okay. And there's your probability P. It's figured as the proportion of successful outcomes to total outcomes, ranges from 0 to 1. And the normal curve can be used to determine the probability of scores falling within a particular range of values. All right, let's hit it. So, probability, z-scores, and the normal distribution. The normal distribution can also be thought of as a probability mathematical distribution. Now, this is that Gaussian curve that we introduced there way back when. And this includes all of the data points of a particular study, however many there are, okay? And you'll see that the mean Mean, median, mode is all, in this case here, all the same, but we just look at the mean. And the mean is that central axis. Okay? Now, that is the mean. That is where the majority of people are thinking. So, now, this is just a histogram, right? It's all continuous. There's no gaps. It's not a bar chart. Histogram. So, a histogram or frequency distribution, that is unimodal, symmetrical, and bell-shaped. Very commonly seen in behavioral studies, psychology, these kinds of things here. And you guys did very well in the last test concerning this. The whole idea here, sorry for jumping around, but you'll see there that your mean, and when you do these, you're actually going to have two scales at the bottom. You're going to have your first scale, so there's your mean, okay? And then you're going to have your first standard deviation, second standard deviation, and third standard deviation. Corresponding percentages, right? We've seen these numbers there before, 34%, okay, 13.5%, okay, 2.14%. You also have the same corresponding values on the left side of the chart, right? So there's your mean again. There is -1 standard deviation, -2, -3. The distance between +1 and -1 is the same. You'll see the percentages here, okay? So when you're doing these here, you're going to have your one scale that's going to detail your standard deviations and where they lie, okay? Because that is very important. And as well, you are also going to have your real numbers. Like this study here, I don't know, maybe it was looking at the number of popsicles eaten in a given day by a particular population. Well, in this case here, the average number was 3. So, you're going to have your one scale here detailing your standard deviations, but then you're also going to have the real numbers, which you guys have been doing very well on your quiz 2 and test 2. Okay, so in this case here, the average number of ice creams was 3. Okay, you'll see there that you're, in this case here, the standard deviation, in this particular case here, standard deviation is 1. It works out on the same on both scales here. It's not always the case though, right? Your standard deviation would be 150, which means you'd have to add 150, add 150, add 150. But in this case here, we just add 1. So the first standard deviation there, we're at 4. Okay, 5 and 6. These numbers here are increasing. These numbers here are decreasing. So therefore, this one here would be 2, 1, and 0. These are your real numbers here. All right. So, just continuing on to what we were just talking about there, the researchers compared the distribution of their variables to see if they approximately follow the normal curve. Because if they do, then amazing things happen, right? And it's all about the sample size. If you have a sample, generally I think it's in and around 30 is the magic number. If you have a sample size there that is less than 30, then you'll have to use something there called a t-test. It's kind of similar, but it's a little different. But if you have what's called this Gaussian curve, now you can start to compare apples and oranges because you have enough participants in your study that any type of study you do with enough participants should come up with this Gaussian curve. The normal curve is sometimes mentioned in the context of describing a pattern of a score of a particular variable. The percentages of scores between two z-scores is the same as the probability of selecting a score between those two z-scores. Haven't introduced what a z-score is yet, other than the fact there you see your standard deviations. You have 1, 2, these are what we're talking about, z-scores. Okay, we'll show you these there in a little bit. So, in behavioral and social sciences, scores on many variables approximately follow a normal curve, which is bell-shaped, symmetrical, unimodal. Mean, median, mode are all equal, located at the center of the distribution. 50% of the scores on the normal curve are above the mean, 50% are below, right? So if you add these numbers up, 34, 13.5, 50%. 50%, right? Half of the values are less than the mean, half of the values are greater than the mean, okay? So a normal curve table is used to determine the percentage of scores between the mean and any particular z-score, and the percentages of scores in the tail for any particular z-score. Blah blah blah. We're going to get into that. Okay. I don't want to make it sound more difficult than it is, because it's really not. But if you're just reading these words here, man, I tell you, statistics can get the wording. Ugh, but we'll show you. I'd rather show you than tell you. So, why the normal curve is commonly found in nature? It's all about your sample size. Okay? If influences are truly random and the number of different influences being combined are large, a precise normal curve will result. Statisticians there call this what we call the central limit theorem. So you gotta have a big sample size. So as the sample size gets large enough, what happens here is you get this heightening, you get this unimodal shape. It's very symmetrical and bell-shaped, okay? Where you have the mean median mode here, where we just look at the mean. So the mean here, this is our central axis, measure of central tendency. And then now, based on the standard deviation, we can see the spread. And we'll show you guys these here, okay? So, why the normal curve is commonly found in nature? Again, a person's rating on a variable or performance on a task is influenced by a number of random factors at each point in time. Noisy room, hunger, amount of sleep, whatever it is here, okay? These factors here can make a person rate things like stress level or mood as higher or lower than what they actually are, or even can make a person perform better or worse than they usually would, right? So these factors here, they can influence and will most definitely affect a person's scores about how they feel about a particular attribute. Most of these positive and negative influences on performance or ratings cancel each other out, in fact. Okay, and now, yeah, noisy room, that can bother, hungry, amount of sleep, these kinds of things. But if you ask enough people, it will balance themselves out, and you will get this Gaussian curve, right? Most scores will indeed fall towards the middle. Whatever the middle is, you know, if you're talking the number of oranges eaten, the number of cars bought over a particular lifetime, the number of toothbrushes, you know, bought, whatever it is, wherever the medium is, the numbers will tell you. And that's where the majority of people will reside. And then things will start to trickle off as we get to the extremes in both direction. Okay? This result is an approximate normal distribution, unimodal, symmetric, and bell-shaped. Okay? So many continuous variables have distributions that are bell-shaped and are called approximate normal distributed variables. The theoretical curve, called the bell curve, or what we call the Gaussian distribution, can be used to study many variables that are not normally distributed, but are approximately normal. Now, this is the formula there that we're going to... No, I'm joking. I would ask you guys this, but I just wanted to show you guys there that there's some heavy-duty science involved here, okay? The mathematical equation there for the normal distribution, yeah, it's a good one. Okay, do not worry about it. I'm not going to ask you guys to calculate that. Okay. The shape and position of the normal distribution curve depends on two factors and two factors only. There is the mean, the axis, the measure of central tendency. Where is that Gaussian curve on this axis? Okay. As well, there is the standard deviation, the spread of the data. If you have a look here at the brown curve, it's more narrow, right? Like your first standard deviation somewhere in here, right? Second standard deviation here, third standard deviation out there. You can see there with the blue curve, the standard deviation is more spread out. the standard deviation is larger, right? The first standard deviation, what's the value in, and then add another one, and what's the value right in here. You'll see there that the blue is more spread out, so it has a higher standard deviation. Okay. Each normally distributed variable has its own normal distribution curve, which depends on the values of the variable's means and standard deviation. So in this case here, I have two populations, and they have exactamundo the same mean. Okay, so you're thinking two populations, same mean. Oh, that's pretty interesting, because that's rare. What, for two distinct pops to have the same mean? That's an interesting statistical analysis point to look at. But you can also see there that these two groups of people are not thinking exactly alike. You look at the people there asked in the brown curve, they're thinking more alike, right? Because it's tighter. All right, it's tighter along the central axis, the mean. So more people are thinking there towards the mean. But then you look at the blue curve there, that's more spread out. You have less people, okay, dragging there towards the mean, and they're more being pulled out to the extreme. So in the blue curve, people are thinking a lot differently than in the brown curve. Okay. Again, just showing you guys the same thing here. In the top example here, they have different means, but the same standard deviation. So maybe we're talking about the number of cats owned, the number of dogs owned, and they both populations there, they have different means, but the standard deviation, you can see there, they are the same curve. And having the same standard deviation means you could take this curve, lay it on top of that curve, and it would completely cover it. Same standard deviation. And in the second example here we have different means. There's the mean 1, mean 2, as we had up here, and you'll see there that the standard deviations are in fact different as well. Okay. So normal distribution properties, the curve is continuous. There are no gaps. This is a histogram, you will remember. Okay. For each value of x, there is a corresponding value of y, right? X, y, they meet at a point, and the point is on that curve, right? The curve never touches the axis. There's what we call an asymptote. It just approaches the line, but never ever touches it. So theoretically, no matter how far in either direction the curve extends, it never touches the x-axis, but always gets increasingly closer. All right, let's go. So the normal distribution properties, you guys have seen this slide there before. This should be kind of nicely familiar, which is why I kind of I throw it there a couple weeks prior, just to show you guys the exposure. Okay. You have there the total area under the normal distribution curve is equal to 1 or 100%, right? Now remember there, this is 34.13%, but you remember there that we can write that as 0.3413, right? And please know that that is the same number as that. Remember that slide there from last week there, the whole idea, you've got to be able to flip in and out of fractions, decimals, percentage, and even ratio. Okay, so that's what we're looking at there. The 68% of the population is within the first standard deviation, positive and negative, right? Then you have about 95% of the population, okay, is within 2 standard deviations. And then you have 99.7% of the population there that is within 3 standard deviations. We don't really go outside of 3 standard deviations. Shaquille O'Neal's shoes are out here somewhere. You know what I mean? The outliers generally, and it's all depends on the business model. Maybe Pepsi, Coca-Cola, Nike, they're interested in, of course they are, because of gaining the attention of the most people. All right, you're going to sell the most shoes, the most Coca-Cola, whatever. Some businesses, they are only interested in the outliers. Okay, I don't know if you've ever seen big and tall stores, where they sell extra large dresses, extra large suits, extra large shoes. These guys here, they're only, curtailing to the outliers, but, it tends to be pretty expensive, I would assume. So, again, probability, the area under the curve. Okay, so again, just showing you guys these percentages there. You've seen them there before. You have your two scales, one denoting there your mean and your standard deviations. And your 3 in your positive direction, 3 in the negative, and then you have your corresponding real number values that relate to the numbers from your study, whether the number of chocolate bars eaten or whatever. Okay, that information is not within this first scale. The first scale is only detailing where the standard deviations are. Okay. So the standard normal distribution there was developed to compare different populations, so we can actually compare apples and oranges. It's crazy, eh? Similar there to the normal distribution, except that the total area, okay, under the standard normal distribution is given as a value of 1. So the area under the curve for a particular range of scores is equal to the probability of the range of scores occurring in the population. Okay, probability equals the area under the curve, and we're going to show you that. Now, do you guys have your Z table? Did you print it off? You're going to need it. Okay, so pause the video, go and make sure that you have that Z-score printed off, the Z-score table printed off. Okay, because this is where we're going to get into it. Ta-da! So, Z-score is equal to the number of standard deviations. This formula right here, Z-score is equal to the value, a data point minus the mean divided by the standard deviation, which corresponds there to this formula here. Z is equal to x minus mu, all divided by sigma. Okay, again, you're going to calculate, these particular questions there. We're going to give you the mean. We're going to give you the standard deviation for the most part. Okay, we're going to give you the data point, and then you're going to do this, and you're going to get a value there for Z. This Z value is going to be right here. Now, this is 1 standard deviation. This is 2 standard deviations, 3 standard deviations. Where would 1.5 standard deviations be? Positive 1.5, well, there's 1, 2, so positive, so it'll be right in about here, whatever that measurement is. What if I went negative 2.5 standard deviations? 2.5, well, there's 2, 2.5 would be in there somewhere, whatever that value. So this is what we're talking about when we're dealing with Z-scores. Z-score is going to tell you the number of standard deviations away from the mean a particular data point will be. We'll show you that. Let's go. But before we do that there, let's have a look. Area under the standard normal distribution curve. Now, this one here, I do not want you to use your Z table. Okay, well, you can't. I didn't give you any numbers yet. Okay, but this one here, I want you guys to guess. Now, you remember, all right, the whole idea here is what percent, now in this case here, there's your mean, and a mean of 0, right? We're dealing with this guy right up here. There's your mean of 0, and then a standard deviation of 1 and 2 and 3. Okay, so here's my mean of 0, and here is this particular Z-score, which is just a standard deviation. Now, these standard deviations 1 and 2 and 3, those are nice numbers, but you can have 1.5 standard deviations. You can have 0.75. You can have negative 0.6 standard deviations. This is just your guide. Okay? So, have a look here. So I have this Gaussian curve, and I have this Z value here. So this is standard deviations. So there's like my, and we're just looking right here. This is here for a reason. So you're looking at the first standard deviation about halfway down the hill, so about halfway down the, so there's standard deviation of 1. So, and I would say there that this guy isn't at 2, but it's somewhere in between 1 and 2. Somewhere in here, right? But we don't know that. And I'm just asking you to guess what percentage of the area under the curve here is being represented. Well, this side here is 50. Has to be. No doubt about it. As we say in Canada here, no doubt about it. All right? And you've got this guy here. Well, that appears to be past 1 standard deviation. So that's got to be 34%. And there's a little bit there as well. So 50 plus 34 is 84%. Plus a little, maybe 90 some odd percent. It's so important to be able to estimate, because you're going to be doing these calculations and the calculator is going to be spitting out a number. You have to know, what's the word? You have to anticipate, be able to know that you're kind of in the ballpark here. And we'll show you guys this stuff here. You look at this one here, a negative Z-score. I'm only asking you to guess what percentage of this. So where are we here? We're probably in this range right here, so we're probably looking at about 2%. And you would be right. That's all I want you guys to be able to do. So I'm going to be asking you questions there to find the probability, right, area under the curve, to the left of a Z value. Okay. I could ask you there to find me the probability, okay, to the right of a Z value. So in this case here, what do you think, just a guess, what do you think that percentage is? Well, again, break it up, right? So that's 50% of the population right there. Again, 34, maybe a bit. So you're somewhere, 50 plus 34 is 84, plus 10. Maybe you're into about 95. Somewhere in there anyway. But just judging by it, you're in and around all of this guy right about here. You have this one here. Now, sorry, notice that was a negative Z-score. But the area is always, it's always a positive area. There's no, when you're talking about probability, there's no negative probability. Okay, we have a positive side to the graph, a negative side to the graph, and when you're talking area under the curve, it all means the same. So in this case here, 50%, 80, 34 plus 10, maybe somewhere in there, 94, 95% total. You look at this one here. The area to the right of this particular Z value, this is a positive Z value, probably 1 point, maybe and about maybe the second standard deviation. So you're looking in and around, there's about 2.28% over here. Okay, just judging by the numbers. So you can go to the left, to the right. You'll need to be able to do this there for your assignment that's out right now as well. This one here, double the trouble, but double the fun, right? I could ask you there the probability between two Z values. So here, just zooming on in, right? Here I have, there's my mean, my 0. Okay, here I have a negative Z value because it's, it's in the negative side, the left-hand side. And here I have a positive Z value because it's in the positive side. And I want to know the area under the curve between that Z and that Z. Or I want to know the probability between that Z and that Z. And then I've got this one right here as well. Here I have negative Z1, negative Z. I want to know the area in between there. All right. So just looking at these there, they're a little bit more difficult to judge, but you're probably looking at, there's 1 standard deviation. So there's 34% there, maybe an extra 10 there. What do you think? That's maybe 20. So somewhere in around 60% or so, I would assume, just off the top of my head. That's and I don't want to harp too much about it because I'm not going to ask you guys to guess and then answer based on that guess. I'm going to ask you guys to guess so that when you do calculate your answer matches your guess and you got your 100%. That's the only thing that matters to me. Okay, So that's why I'm showing this to you here. Being able to guess the percentage in and about. Doesn't have to be exact, but you have to know that that ain't 20%. That's in the 90s, somewhere in there, roundabout. It's, if it's not on that second standard deviation, it'll be right somewhere in there. Okay? So you can go to the left, to the right, in between. Lots of stuff here I can ask. Very, 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 very important concept. And we've alluded to this already there, that the area under the curve, right, the probability is 1 or 100%. Okay, so the probability, okay, on this side of the graph makes sense is 50%. On this half, 50%. And remember, we're dealing with percentages, even though that's a decimal. That's how we write these things. Okay, so that's 50% on this side, 50% on this side. Now, an even more important concept is when you are calculating these z-scores, right? These guys right here. Z is equal to the value, the data point, minus the mean divided by the standard deviation. Pretty simple formula, okay? But the premise is based on this, okay? The most important slide, you want to get this right. This is the slide there that will lead you in the right direction. The Z table counts, okay, half left to right, starting from the mean. And we're going to show you this there. Well, I'll show you there in the next slide there, the whole idea of the Z table and how it works. But when you are calculating the area under the curve, which is what you're going to be doing, it goes from here to out, or here to out. Everything starts from the mean. And it won't make sense right now, but if you can just put a pin in that, okay? When you're calculating the area under the curve, okay, the Z table measures from the 0 line to that data point. The 0 line to that data point, okay? Always starts from the middle, and I'll show you guys this there in 2 shakes. So, here is the Z table, okay, that is provided for you there in the week 12 folder, okay? And just kind of zoom in here and just show you guys here what's going on. The whole idea there is this is your standard normal curve with your mean of 0, standard deviations of 1 and +1, -1, +2, -2, +3, -3. Nothing new there. And we just calculated there for the number of apples eaten in a 24-hour period on average for this particular population, and we got a z-score for this particular population, I don't know, 1.3, positive 1.3. And you got to say positive, right? Because negative 1.3 is over here. So what we're going to do now is we're going to measure the probability, okay, based on that particular z-score that we calculated. Where does it fall into everybody else in the number of apples there that they've eaten? Okay, so what does all this mean here? So after calculating the z-score, which we haven't done yet, but it's the easiest of them all, how do you find the area under the curve, or the probability? Okay, you remember there the z-score is equal to the number of standard deviations away from the mean, right? And let's go back here to our little graph, right? The z-score is the number of standard deviations away from the mean a particular data point falls. That's all this is. How far away from the mean we're counting in standard deviations. So you'll see here that you're going to calculate a z-score, and we're going to show you. So your z-scores are here in yellow along the top. If I wanted to calculate, I got a z-score of 1.5. Well, I would go 1.5, it's right there, and you see 0, so 1.50. So the probability for this particular z-score at 1.5 standard deviations is 43.32%. Okay, we could go to 2 standard deviations. I could go to 1.75 standard deviations. 1.7 right here. Go across 0, 1, 2, 3, 4, 5. There's your 5 right there. So 1.75 is 0.4599. So there's a 45.99% chance that that event will happen at 1.75 standard deviations. We'll show you these. What if you get a negative standard deviation, right? In this case here, I got a positive Z. What if I had negative 1.5? Negative 1.5, and I wanted to find the area of the curve. Negative 1.5, cancel the negative and just go 1.5. There's your 1.5, so 0.4332, 43.32%, right? And it's the same. The probability, there's no negative probabilities, okay? If you're trying to find the area under the curve on the negative side of the graph, okay, acknowledge the negative, but when you're looking, when you have your Z-score, you change it there to a positive and calculate it as such, okay? As well, so your Z-scores are along the sides, okay? You're never going to have a Z-score there that is bigger than 3.4, okay? Just the way it goes. Why? Because these are standard deviations, right? And look, 1 standard deviation, 2 standard deviation, 3 standard deviation. There's Shaquille O'Neal's shoe size out here, 3.4. We don't deal with any of these guys out here. You can have 4, 5, 6, 7. You can, all these different standard deviations, but it gets kind of pointless because within 3 standard deviations, what's the percentage of the pop? 99.7%. I'll take it. So we don't really go outside of 3 standard deviation or the 3rd standard deviation. Okay. Now, your Z values here, right? There's a little Z. You can see it. These are your Z values here, standard deviation values. And then you look for the area under the curve. Sorry for jumping around here. You look for the area under the curve. And you'll notice here that these are all percentages. These are all the areas under the curve. And you'll notice here that the highest value is 0.4998, 0.5. And that's what we were talking about there earlier, that the Z table only counts half. Okay? So if you're dealing there with an area under the curve, you're only dealing with half. All right? It doesn't cover the full table, or it doesn't cover the full graph. So that's why when you're dealing with the Z table here, it only details half of the graph. That's why we start from the middle and work our way out, because that is 0.5, that is 0.5. All right, enough chat. Let's have a look here, please, and thank you. What I want you guys to do now is the answers are all there. You can see them in red, okay? But what I want you guys to try here is I want you guys to try and figure out what these areas of the curve are. So here we've got their Z table. Actually, and I'm going to take one of these guys here. Good. So now I want to know the area under the curve, the probability, where Z is equal to positive 1.8. So where is positive 1.8? Somewhere in that direction right there. Maybe 0.2, maybe even a little smaller, right? So this is 0.18 of a standard deviation. That's 1, 2, 3 in the positive direction. Here, this is positive 1.8, so 1.8 is in here, somewhere, okay? Not really important there that we need to know exactly where it is, but just as long as we have a figure, and you'll see the percentage involved. Okay, remember we're counting from the 0 to that line, 0.18. So let's have a look here. 0.18. So now Z score of 0.1, I'll zoom in a bit more. Sorry, jumping around a lot. 0.18. So 0.1 is right here. Go across 0.11, 0.12, there is 0.18. So that percentage there that we looked at, what was that? 0.0714, 7.14%, right? So that area, and I'll just spin this around here. See that area right there, right, that we kind of covered up, right? Because that's where the 0.18 was, right? One standard deviation, so half a standard deviation would be over here. This is about 0.18, so that area under the curve is equal to 7.14%. Look at this one, Z is equal to 0.4. So now let's go, where would 0.4 be? Now that's a positive direction, right? So 0.4, well there's half, that's halfway through, right? So 0.4 would be a little bit less, so somewhere in there, maybe that's 0.4, right? So this whole area, right, that's the 0.4, and we want to know the probability of that. Now that was 0.18, that was smaller, and that was 7%. This is 0.4, so I'm anticipating there that my probability is going to jump. Why? Because there's more area under the curve. So now Z is equal to positive 0.4. Now when we're looking up our Z, we don't need the positive or negative. Everything is positive. So 0.40, aha, in this case here, 0.40, we were indeed correct. Our probability, okay, has gone up, right? Because there's more area under the curve, and in this case here, 15.54%. Look at this one. Z is equal to negative 1.96. So in this case here, let's flip this, right? And straighten it out if I can. So 1.96. So that is almost 2 standard deviations to the left side. So where are we here? So we're about there. It's not exactly touching, but we're looking for all of this area under the curve to about here. So remember, we're always starting from the 0 line. So because we're going in the negative direction, I'm not dealing with this side here. I'm dealing with the area under here down to about here and then down. Does not include, so there's a little strip right here that I'm not including. I want to know what this area is. So you're looking at it here, definitely going to be greater than 34% because it encompasses the entire area, and it's almost all of 13.59, maybe it's 12. You know, there's just a little smidgen there that's left over, you can see it. So 34 plus 12, I'm anticipating a number somewhere around 46%. Let's see how right we are. And I have no idea. I could be way off. I don't think so. Let's have a look here. So negative 1.96, that's my Z value. I'm not worried about the negative. I only look at the positive here. So 1.96. Zooming in. 1.9, right? Well, 1.9, 0, 1, 2, 3, 4, 5, and 6. So 1.96. Here I've got 0.4750. That is, and what did we say? 46%? And we got 47.5%. I think that's a 6. Yeah, it is a 6. So in that case there, okay, the Z value, sorry, that one there should be 147.5 right there. Good. All right. So, and again, 47% probability because of a greater area under the curve. Let's have a look at the last one here. Z is equal to plus 2.55. So you have a look at where we're at. plus the area there is, now we're in the positive direction, right? And I'm going to move that over there. So we're looking at two standard deviations, right? So there's one standard deviation, two standard deviations. We have 0.55, so we've got to go 0.55 over. So now we're looking at the area under the curve almost half. Like it's almost half, right? So we're looking for all of this area under the curve. So it's definitely going to be 34%. It's definitely going to be 13.59. So what are we looking at here? 34 and 14 is looking at 38, 39. 48, 49%, somewhere in there. And let's have a look at what. And when you're doing these, remember, it's not